Ever wondered about that? How can you single-handedly lift a car or crack open a super tough nut with barely any effort? It honestly feels a bit like magic, but it's actually something way more fascinating. It's physics.
So, let's dive into the physics of everyday magic. In this explainer, we're going to pull back the curtain on all those invisible forces that are constantly shaping our world. And you'll see, physics isn't just some boring subject you learn in school, it's basically the instruction manual for reality itself.
So, back to that first question. How do we multiply our own strength? Well, the answer isn't about hitting the gym and using brute force. Nope, it's about being clever. It's about using simple machines to amplify our effort, making us way, way more powerful than we look.
Right. The secret here isn't about becoming a superhero. It's about using a fundamental principle of physics to your advantage, and it's called the moment of force, though you probably know it by its much cooler, common name, torque. It's the absolute key to understanding pretty much any turning effect. And just look at how simple this idea really is. You've got a pivot point, right? That's marked here as O. When you apply a force, that's F, at some distance from that pivot, you create a turning effect. And that amazing combination of force and distance, well, that is torque.
What this all means is that torque isn't just about how hard you push. It's also, and this is crucial, about where you push. The official definition is that it's the product of the force and its perpendicular distance from that pivot point, or the axis of rotation. And here it is, the secret sauce, in a super simple formula. Torque equals force times distance. So think about it. To get a job done, you have a choice. You can use a massive force over a tiny distance, or you can use a small, easy force over a much longer distance. The moment you increase that distance, d, the force F that you need to apply, just drops like a rock. And you see this principle everywhere. Seriously, think about the door to your room. The handle is put on the complete opposite side from the hinges, right? That's the pivot point. This maximizes the distance, so you barely have to push to swing it open. Or picture a mechanic trying to get a really stubborn nut off a tire. They're going to grab a wrench, a spanner with a really long handle to make the job easy. More distance, less effort. It's just physics doing its thing.
And we can actually put a number on this force multiplication. It's called mechanical advantage, and it tells you how much bang for your buck a machine is giving you. You just calculate it as a ratio. The load, that's the big thing you're trying to move, divided by the effort, the small force you're actually putting in.
Of course, it's not just about levers and wrenches. Pulleys use these exact same principles. A single pulley is awesome for just changing the direction of a force, like pulling down to lift something up. But the real magic, the really cool part, is when you start combining them into a system. That's how you generate a massive mechanical advantage, letting one person lift something that weighs hundreds of pounds. Okay, so we've seen how physics lets us manipulate huge, heavy objects. But what about manipulating something that has no mass at all? Let's switch gears and talk about light, and let's ask a really simple question. How does a clear piece of glass somehow unlock all the colors of the rainbow? I mean, this is such a classic image, right? A single beam of what looks like white sunlight goes into a prism, and out comes this incredible full spectrum of colors. This beautiful phenomenon of splitting light is called dispersion. But why does it even happen?
So let's follow a single ray of light on its little adventure. As it hits the prism, it goes from moving through air to moving through glass, and that change makes it slow down and bend. That's called refraction. But while it's inside the glass, something really important is going on. Then, as the light leaves the prism, it speeds back up and bends one more time on its way out. And this incredible fanning out of all the colors has a name, dispersion. And it's not just something you see with prisms. This exact same process is the reason we see rainbows. You've got millions of tiny raindrops hanging in the air, and each one acts like a miniature prism, splitting the sunlight all across the sky.
So here it is, the solution to the whole mystery. Not all light travels at the same speed when it's going through glass. The speed actually depends on its wavelength, which is what our eyes see as color. So each color bends or deviates just a little bit differently. Violet light slows down the most, so it gets bent the most, while red light is the speed demon. It's the fastest, so it bends the least.
All right, so we've established that light behaves like a wave. But it's definitely not the only kind of wave shaping our world. So now let's broaden our view a bit and explore the physics of a wave that we can't see, but we can definitely hear: sound.
We've all experienced an echo, right? You shout into a canyon, and a moment later, your voice comes back. It's just sound bouncing off a distant surface. But here's a fun fact. For you to hear a really distinct echo, a separate sound, there are rules. Your ear needs at least 1/10 of a second between sounds to tell them apart. And for that to happen, the thing the sound is bouncing off of needs to be at least 17 meters away. If it's any closer, the sounds just kind of blur together into what we call reverberation.
This little table really shows you just how different sound and light waves are. Sound waves are longitudinal. Just think of a slinky pushing forward and compressing. Light waves, on the other hand, are transverse. They move up and down, kind of like a ripple on a pond. And look at the other differences. Sound is, well, pretty slow, and it needs a medium, like air or water, to travel through. Light is unbelievably fast and needs no medium at all. It can just zip right through the total vacuum of space, which of course is why we can see stars that are so far away.
From the visible world to the invisible, let's now take a journey to the infinitesimally small. We're going inside the atom itself to find a source of power so immense it almost defies belief.
Okay, quick refresher on what an atom looks like. At the very center, you have this tiny, incredibly dense nucleus made of positive protons and neutral neutrons. Then you've got these negative electrons orbiting around it. But here's the key takeaway, the mind-blowing part. Almost all the mass of an atom is packed into that teeny tiny nucleus, and the rest is mostly just empty space.
But here's the thing. Not all atomic nuclei are stable. Some are constantly trying to get to a more stable state, and to do that, they spontaneously decay. They literally throw off particles and energy as radiation. This whole process is called radioactivity, and it's so important to remember. This is a nuclear phenomenon. It only happens in the nucleus. The electrons whizzing around on the outside have absolutely nothing to do with it.
And this whole thing leads to one of the most mind-bending ideas in all of science. When scientists were measuring these nuclear reactions, they found something that seemed impossible. The total mass after the reaction was always a little bit less than the mass before. A tiny bit of matter was literally vanishing. So, where did it go? Well, back in 1905, Albert Einstein gave us the answer. The mass wasn't gone. It had been converted directly into a tremendous amount of pure energy.
And this right here is the heart of nuclear power. You are literally witnessing the conversion of matter into energy. It's about taking a tiny, almost immeasurable amount of mass and unlocking a truly colossal amount of power. It is the very same principle that fuels our sun and every single nuclear reactor here on Earth. So from levers that make us super strong, to prisms that unlock the rainbow, all the way down to the immense power hidden deep inside the atom, physics is really just the language that describes the reality all around us. It replaces mystery with pure understanding. And that just leaves the biggest question of all. What magic will it help us explain next?